So good. So I guess the last time was like really introductory. It was more or less like statistical mechanics 101. Today we'll dive a bit more into details, I guess, but we did, manage to at least define our framework a little bit. And the first thing we're going to do today is show how the notions in our framework basically give rise to a very, to my opinion, a very simple proof of this framework by ALO. So Nima, Anari, Kui, Liu, and Oveis Gharan. And let's start by reminding ourselves what we had last time. So our setting is the following. We have some state space omega. It can be anything, actually, but we'll usually talk about the cases Rn or the discrete hypercube, okay? And we always fix some probability measure on omega. This is the probability measure from which we want to produce a sample algorithmically. Okay, so, and we had a few examples last week. We considered the Ising models where the potential is some quadratic function, or the hardcore model where you basically want to sample an independent set in a graph, or log-concave measures in Rn. We just had a few examples to kind of motivate the families of distributions we care about. And the objective is to produce a sample. And how do we do that? Well, here we do that using a Markov chain. So P is usually going to be a transition kernel of a Markov chain such that P of nu is nu itself, meaning nu is the stationary measure. We're also going to assume it's the unique stationary measure. Doesn't matter so much. This will kind of follow from our proofs. But the point is, if we have a transition kernel like this, then a natural algorithm for sampling is just start from any fixed point. This basically gives us some random walk on our state space, and we just run this random walk, and hopefully at a large enough time, what we have is more or less a sample from our measure. And this motivates us to define the mixing time of a Markov chain, which is the following thing. It's the smallest time such that, so this is the mixing time given a Markov chain, some epsilon, and a starting measure mu. Suppose I can produce a sample from some fixed starting measure. I take mu and I run t steps of the random walk. I get some measure, and I want this measure to be close to nu in total variation or L1 distance. This just means that for any subset of omega, the measure this gives to the subset is close to the measure that this gives to that subset. And I want it to be less than epsilon for every such subset. Okay, so this is the mixing time. And by slight abuse of notation, the mixing time without a starting measure is just going to be the worst mixing time over all starting measures, which are just fixed at one point. So delta sub x is just a Dirac measure that's just supported at one point x, and I look at the worst starting point, and I want to kind of say that the mixing time is not so bad for any point. Okay. Now, how do we prove bounds of this? So a very natural kind of way to do it, a very useful way to do it is by functional inequalities. And maybe the most basic functional inequality is a spectral gap inequality, which basically says, let's look at P as an operator. For us, we'll actually only consider self-adjoint operators. So this is, we can diagonalize this and then look at all test functions which are orthogonal to the all one test function, which kind of represents, sorry?
Yeah, on omega.
On omega. Yeah, phi is always going to be a function from omega to r. Yeah. And this basically says that so by this equality, it's kind of clear that if I take phi equals to all ones, I still get the all ones function.
All ones is mu.
All ones is mu. Yeah, phi is kind of like a change of measure with respect to mu. So phi is like
the integral as a sum, just to the integral, like just to, for a.
This one. Yeah, I mean, I kind of, you know, this is a more compact way to.
No, I'm just trying to figure out.
But it is. I mean, you know, it could be on our n, and then you know, it's actually an integral. But yeah. So this is just invoke p on phi, and here we just have the L2 norm of phi, and we want to say, you know, how much p shrinks the L2 norm of anything other than the all ones vector, basically the Perron-Frobenius eigenvector that we know that it doesn't shrink. Okay, so I guess we all know this from just random walks on graphs and stuff like that. And a basically folklore, easy to prove fact is that if we have a lower bound for the spectral gap, then we have an upper bound for the mixing time, and it looks like basically the spectral gap inverse. And here we have something which is sometimes annoying. It's the log of the mix I wrote. It's min. The log of the minimum basically density at a single point. So this is only useful if I know that every point x is assigned some probability. And if this looks like, you know, this usually looks like e to the constant times n, and then, you know, you will get the log of this will be poly m. But sometimes this is, I mean, if you want to get optimal bounds, this is usually not going to be good enough. We'll discuss it later. But anyway, if you just want to get some poly m bound, then this is almost always good enough. And we also get a logarithmic dependence on epsilon. The proof of this,
So
I guess.
mix p epsilon.
Yes. Thanks. Any questions about this? I guess there's really nothing new here. Now let me remind you about our framework. So this is basically, you know, the new framework that I started telling you about last time.
Maybe we should like your course's name.
Right. Thanks. So this is all joined with Yuanzi Chen. And in the center of the framework is kind of an abstract definition that works for really any state space you would want. So not just these, but we'll only talk about these, like Rn and the discrete hypercube. And the central definition really is a localization process and a localization scheme. What's a localization process? It's a process, stochastic process valued with measures. So at every time t, we actually have a probability measure on the same space, on omega, okay? And as a stochastic process, it has the following property that for every subset of omega, I can look at the process nu t of A. Okay, so now this is a real valued stochastic process. And what I want is that this thing is a martingale. Now, since those are probability measures, it's a martingale taking values between 0 and 1. So if you know the martingale convergence theorem, that doesn't matter so much if you don't, but it converges to some value, definitely, as t goes to infinity. It can't move forever with probability 1. But what I want is that it doesn't converge to just any value, but it converges to either 0 or 1. So basically, for every set A, nu t is either all inside of A eventually or all outside of A. eventually. It can't be like half and half. And it's not very hard to see that in some sense this says that we basically converge to a Dirac measure as time goes to infinity. I mean, basically in a weak sense, if you want. Questions about this? This is really the central definition. So if you haven't digested it, this is the time to ask questions.
And this Dirac measure is like a sample.
Yeah, so you can think about this Dirac measure, thanks, Avi, as a sample. So, I mean, this can be thought of as a very twisted and convolved way to sample from our measure. If we could actually run this thing algorithmically, which we do not intend to, by all means, at any point, this is just for the sake of analysis, then we can just run this up to the time in which it converged to a point. And this point actually has to be distributed according to the original measure. Let me actually write this. I think we're not going to use this at all, but just I think, you know, it's pretty important for the understanding of this. So a fact that follows like immediately from this definition is that, well, maybe let me, nu at time infinity, whatever that means, is basically equal to delta at some point x, and x is nu distributed. Yes.
So actually, now that you mentioned, I'm somewhat curious, why don't you use this to sample from nu? I mean, I remember from last time you.
How do you?
Well, I mean, there was this SDE. I mean, I thought that in some cases there's.
He will go back to what he said last time, but at this point there is no mechanism to implement this process.
So, I mean, it's a great question. I mean, maybe in some settings there is a mechanism to implement this process and it actually gives something. And like about a week ago, I think since my last talk, a paper has been put on the archive by, okay, I'll just say the name. So Andrea Montanari, Ahmed Al-Alawi, and I'm sorry, I'm not doing the order right, and Mark Selke. And they actually use stochastic localization, which is one of the processes that I'll show you, to sample from the Sherrington-Kirkpatrick model. So actually, sometimes this is actually useful to run this thing. But yeah, I mean, for most cases that we're gonna discuss today, it's not so clear how to efficiently, you know, you kind of need to, even just to have this measure nu t in your computer's memory. It's a measure on like 2 to the
high-dimensional measure.
Yeah.
Thank you.
So yeah, we're gonna mainly discuss high-dimensional stuff. So yeah, and it's big.
Exponential dimension, not just high.
So yeah,
it's defined.
Right. Nu lives in a dimension which is exponential in the dimension of omega. Yeah, I mean, the space of measures. Okay, so this is a localization process. What's a localization scheme? It's basically an assignment from the space of measures, and to every measure, this gives a localization scheme such that at time 0, I start from the original measure. So it gives me an evolution, a random evolution between some given measure that it kind of evolves on the space of measures and it ends up in a Dirac measure. And this Dirac measure is distributed according to the measure nu. Okay, so but this definition, it's nothing. It's just like the scheme is just, you know, an assignment of the corresponding process to the measure.
But
okay,
is it well defined? Like, is this? There's only one way to do that?
No,
not at all. I mean, so I already gave like a few examples last week. We'll see more examples this week. There's a million ways to do that.
Okay. I mean, it's
okay. Even like more than a million. Yeah. Okay. Good. And then what we saw is that there seems to be a very natural way to associate a localization scheme with a sampling algorithm or with a Markov chain via this very simple formula that basically says, so this definition basically says P of, so given a localization scheme L and some time tau, this is just some fixed time, I can assign to any measure nu a transition kernel from X to Y. And this transition kernel is just defined by this formula. The expectation, this expectation is over the randomness that we have in the localization process. And well, I mean, this is...
It's tau in both
That's
of them, right?
tau, yeah, I mean, it doesn't look so good. Tau, tau. And well, this is just a formula that depends on X and Y and the randomness. And basically what it says is like, to go from X, I kind of look at all localization schemes and I reweigh the path of the localization scheme by this ratio, which is how much density it gives to X relative to whatever it gave X at time 0. So this thing, you can think about it as a reweighing, and then given this reweighing, I just have this measure on Y. So if you want an equivalent way to think about this is the following. You can first sample nu sub t, then sample 2 independent copies of like a point from nu sub t, X and Y. Let me actually write this, because so I can think about it like this: sample nu sub t, sample 2 independent points given nu sub t, X and Y from nu sub t, and then I want that P goes from X to Y, little x to little y is like is the law of well, let me just, it's just the probability that big Y is little y given that big X is little x. So I kind of sample 2 points. They have some joint distribution, which tells me kind of what's the law to jump between points. Okay, and it's not hard to see that this is equivalent to this. And we saw 2 examples, I think, last week. One of them is the so-called Glauber dynamics, which arises as the dynamics associated to the so-called coordinate by coordinate localization scheme, which I'm gonna remind you what it is. It's basically like at time t, take one of the coordinates which you haven't revealed so far and reveal it according to the conditional probabilities. I'll say a bit more about this in a minute, but first,
before this fact, you also proved to us that it's actually a Markov chain.
Yeah. Sorry, I didn't say that, but this is always a reversible Markov chain whose stationary measure is nu. Yeah, thanks. Is nu, which is nu 0. Okay, so questions? I'm going fast over this because we went over this last week, but I realize some of you may have forgotten. So, okay, good. And now here's a useful fact that's just a 2-line calculation. So this gives, you know, the localization scheme gives rise to a dynamics. And now I want to give a lower bound for the spectral gap of this dynamics. I want to say something about this mixing time. So there's actually a way to think about the spectral gap in terms of the localization scheme. And how is that going to look? What is that going to look like? The spectral gap is just equal to the minimum over all test functions. Again, this is a function from omega to r of the expectation of the variance remaining in the test function after I run the localization scheme up to time tau over the variance at time 0. So this is kind of how much of the variance I still keep after running the localization scheme. And let me just this is really a central thing. So let me just like at least the intuition I want you to have. I'm going to kind of repeat what the intuition I gave before. Maybe let's think of test functions which are indicators of subsets. So maybe phi is just, I don't know, the indicator of this. And all of this is my state space omega. And first I had some measure mu on the entire state space omega. And I run the localization scheme, which gives me measures which are kind of zooming in to a smaller and smaller portion of my state space. Okay. We can even think of a localization scheme that at any given time is just, no, never mind. So they're just kind of zooming in. I don't want to give examples. So you know, at time 0, I have the entire thing. At time 1, maybe I have something here. At time 2, maybe I have something here, and I kind of keep zooming in. And what we want to show is that all the way up to time tau, I still see some variance, which means what in this case? It means that I have zoomed in to a place that's not entirely contained here or entirely contained here. I want to say that I have some probability, which is not negligible, to zoom in into a place that kind of sees the boundary of the set. And what does it tell me about the Markov chain? It tells me that if I start from a point in my omega, and I do one step of the Markov chain, well, this step is going to be basically inside the set to which I zoomed in. So if there is variance in this set, it kind of means that I can actually cross in and outside, inside and outside of this like region.
So it's
okay,
still
so this is
boundary even
exactly
time tau.
Yeah, exactly. So this is kind of a local expansion property.
Like what it says it's expanded?
Because it has it crosses every boundary with some fixed probability. This phi is arbitrary. You can think of it as any set. Right. So it crosses any set. Yeah. So it doesn't have small cuts. Only is relative to the measure mu, of course.
Yes. Yeah.
Yeah. If something has negligible or zero probability, you don't care about it anyway.
So the localization scheme kind of gives me the edges of the graph, which are, you know, the local things I see at time tau. And okay, good. So that was all a reminder from last time. And now what I'll do now is still kind of a reminder. Not sure I wanted to erase this. Okay, maybe I'll keep this at least. Continue here. Okay. So now let's consider.
I still will say something I find magical in this. It's that you start from an abstract, this localization scheme, just an abstract dynamics that nobody can implement. And it defines something you can implement, like a Markov chain, or you sometimes can implement. And how fast it converges depends in a very simple way on this abstract, unimplementable.
Yeah. So this is right. So this is just kind of a natural tool to analyze this that we have no idea how to implement, but it gives us insight about the implementable algorithm. Good. So now let me define, which I also briefly mentioned, a natural family of localization schemes that will be very useful for us. So we call it linear tilt localization schemes. And this is just the family of localization schemes such that to go from the measure nu t to nu t plus 1 or nu t plus epsilon, if it's a continuous time, everything here can be in continuous or discrete time. What we do is we take the measure nu t and we multiply it by a linear function such that the gradient of the linear function is chosen random. The randomness just goes into the gradient. So linear tilt localization schemes are localization schemes of the form nu t of x, nu t plus 1 of x over nu t of x is equal to 1 plus x minus the center of mass of nu t. So B nu t, or B for every measure mu is defined to be just the integral of x d mu. So this notion only makes sense of linear spaces. Whenever I have a natural embedding into a linear space, this family of localizations makes sense.
In particular, the discrete cube lives in Rn.
Yes, in particular, the embedding of the discrete cube in Rn is going to be very important for us. Yes. In fact, like this framework really doesn't tell the difference so much between the discrete cube and Rn. Like proofs that work on Rn almost verbatim can like say things about measures on the discrete hypercube. So the randomness is going to come from this random vector zt, where the expectation of this random vector zt given mu t is 0. So and zt takes values in Rn or in the linear space, really in the dual to the linear space. Okay, so this is just a family of localization schemes. Why is the 1 here? And why is this center of mass? Well, it's not hard to see that if I take a measure and multiply it by a function which is equal to 1 at the center of mass, I do not change the integral of the measure. So unless I get negative points by doing this, which I mean we don't want to get, this automatically satisfies the first property that says that I have a probability measure for every time t. Now, this fact, the fact that the expectation of zt is 0 given nu t, exactly tells us that this is a martingale, right? Because the measure, I mean, it basically just says that the expectation of this over this conditioned on this is 1, because the expectation of this is just 0, okay? And for the third property that it converges to 0 and 1, I mean, it'll be some extra condition on zt, which I don't want to discuss right now. It's not very hard to understand what this condition is. It kind of wants to discover all directions eventually. Doesn't matter.
In particular, if zt is 0, which satisfies this condition, you don't move at all. It's not interesting.
Yes, if zt is just 0 all the time, then I have the two properties, but yeah, this is not very useful unless you
want.
Yeah, unless you just want to stare at it and enjoy life, it's not doing much otherwise. Yeah, good. So these are linear tilt localizations. We'll see a few examples of these, but we're going to start with a localization scheme that we already saw last time called the coordinate by coordinate localization. I mean, that's how we call it. So I gave a certain definition last week, but now I'm going to give a different definition. I mean, a different way to construct it, which will actually be much more useful for us. So coordinates by coordinates. Localization, it's just going to be defined via that equation up there. And I just need to tell you what ZT is. So ZT is going to be the following thing. First, we'll generate K1 up to Kn, a random permutation, a uniformly random permutation of the numbers 1 to n, which corresponds to what's the order of coordinates that we are exposing. And now I'm going to define ZT to be, I'll just give you the formula. So it's going to be the KT standard basis vector. So these are just the standard basis vectors, which means that I'm tilting only by a linear function that goes in the direction of one coordinate. And I'm going to tilt it in the unique way that basically is going to pin this coordinate to either +1 or -1, restricted to either +1 and -1. And the choice is, I mean, it really doesn't matter so much what the formula is, but well, the formula is the following. So I'm going to multiply it by, I mean, the vector is going to be 1 over 1 plus b mu t I with probability 1 plus b mu t I over 2 and -1 over 1 minus b I with probability 1 minus b I over 2.
So this is a vector.
Sorry?
These numbers, what is I?
I is the ith coordinate.
So from every.
I is KT. Yeah, sorry. Sorry. So, okay, I mean, I have the discrete hypercube and I have some measure here and I want to pin it to either, I suppose I chose this direction, this coordinate as KT, and then I want to pin it either here or here. And well, the distribution is just depends on the mass here and the mass here, right? If I want it to be a martingale, the probability to be here should be proportional to the mass here, which is also, I mean, given by, I mean, the mass on the left side is, the right side is just given by this, right? The center of mass is just, a linear combination of the masses. So, you can just check that what this does is exactly this pinning, okay?
In terms of this shrinking of the space omega, you go just to subcubes of the.
Yeah, you just
one
keep going to subcubes, and I chose to write it in this weird way that conditioning with subcubes is like multiplying by those linear functions. I mean, if you want to understand why this is like pinning to a subcube, well, if you look at the formula there, I mean, you want to take one of the halves and set it to 0. So if this scalar product is equal to -1 on the subcube, then you will have +1 and -1, which is 0. And if you take one plus, you know, this KT coordinate, you will have like -1 minus the KT coordinate over 1 plus the KT coordinate, which just pins to which is just -1. Then you have 0. I mean, it's really just straightforward to check. I feel like I don't have a better way to explain it than, okay, just let you stare at it for a second. Okay, so I wrote it in this strange way, and this gives rise to what we call the Glauber dynamics, which is just if we take tau to be n-1, so P of the coordinate by coordinate and time n-1 of nu is just the Glauber, what we call Glauber dynamics of nu, which is just defined as every time you generate a coordinate and then you change this coordinate according to the conditional probability conditioning on all the other coordinates. Okay. So, I mean, if you don't exactly remember what that is, this gives rise to a chain that's very easy to algorithmically implement. And then we want to understand, like, we want a spectral gap for this thing, or in other words, we want a bound on this. Okay. And how do we get a bound on this? Well, a natural definition that we saw like in the end of the last talk is the approximate conservation of variance. So definition, a localization process satisfies epsilon approximate conservation of variance up to time some big T if for all test functions phi and for all times which are at most T, we have that, well, here we want to say the variance did not decay too much all the way up to time tau. Here we'll just look at how much it decays in one step. I look at the expectation of the variance after T plus 1 steps conditioned on what I had after T steps. And I want to say that this is at least 1 minus epsilon times the variance with respect to nu T of phi. So this basically just says, in one step, I don't lose too much. And then I can just kind of, keep using this, use this inequality as a telescopic product, and then I get something like this. Okay, so what we want is to establish an inequality like this for a process that looks like this. So let's try to do that. And we'll try to do that in a way that kind of, the point of what we'll see now is that the covariance structures of our measures along the process kind of very naturally show up when we try to understand, basically calculate what the variance decays are. Okay, and this will allow us to prove this structure theorem that relates between covariances and spectral gaps. Okay, which is like I spent, I guess, half of last lecture given an intuition why we might expect something like that to happen. And indeed, like the Anari, Liu and Oveis Gharan framework shows it. And this gives another simpler proof of it in like the context of the discrete hypercube, but also in other contexts. Okay. So let's try to understand what this is for linear tilt localizations. So maybe let me just rewrite this formula. So let's try to understand what is the expectation. We fix some test function and try to understand what the expectation is of the variance with respect to nu t plus 1 over test function given nu t. So this is the expectation. Let me just write the definition of the variance. Integral phi squared d nu t plus 1 minus integral of phi d nu t plus 1 square conditioned on nu t. Just wrote the definition. Now look at this term. I know that the measure nu t as a measure valued process is a martingale. So this conditioned on this is just nu t. So the first term is just the integral of phi squared d nu t.
In expectation.
Yeah. Okay. What about the second term? So the second term, well, I don't know that it's true anymore because I'm taking this to the power 2. But, you know, let's use the definition of nu t plus 1. Okay. So this is going to be minus the expectation of what? I have the square of the integral of phi x. Now I have d nu t plus 1, which is x, sorry, it's 1 plus x minus the center of mass of nu t, zt, d nu t of x, all of this squared conditioned on nu t. I didn't do anything. All I did is I just replaced nu t plus 1 by this formula. Okay. Good. Okay, now let's try to open those brackets. Okay.
So just to make sure, the expectation now, since you're taking it, you fix nu t, so the expectation is only on ct. That's the only thing that.
Yeah, ct.
Yes, yeah, that's true. This expectation is really only on the vector zt conditioned on nu t. Yeah, yeah. I mean the expectation, like even if I don't condition, is like over z1, z2, z3, etc. But here, since as you say, since I condition on nu t, it's only zt left to kind of generate the randomness from. Good. So now let's try to open these brackets, and what will we have? We'll have, well, I mean, open kind of these brackets. So I'll have nu t times 1, and then square here. So I claim that this will give me, first I have this. I claim that this 1 here is going to give me integral nu t f phi d nu t squared.
That was the original variance.
Which is just, so here I have the original variance. Okay. Now I have the, cross term, which is 1 times the expectation of this, but the expectation of this is 0 given nu t. So the cross term just vanishes. And what I have left is just this times this, which is just, well, it's just the variance of, I mean, again, because this has expectation 0, it's the expectation of the square of this part, which is just the variance of this. So I have minus the variance of the following thing of the integral of phi x minus b nu t ct conditioned d nu t x conditioned on nu t. Okay. I didn't do anything. This is just straightforward derivation. Now, I'm gonna continue here because I don't want to erase this. It actually doesn't. Okay, I'm gonna erase this because it's not gonna matter so much. This, note that this derivation so far has nothing to do with the coordinate by coordinate scheme. It's for any linear tilt localization. This will actually be useful. So I'm going to write it like this. This is equal. So this is just the variance with respect to nu t of phi, which is great because we wanted to compare this thing to the original variance. So whatever we decrease here just needs to be small. Okay. And well, what is this thing? So first of all, on an intuitive level, we do something and multiply by a linear function. This only kind of depends on first moments, right? I mean, this whole quantity as a function of zt is just has to do with b of nu t, which is the center of mass of nu t, and some kind of like integral x d mu t, which is a first moment, but it's not going to be of nu t, it's going to be of nu t times this phi. So you want to say that like the first moment does not change so much when we multiply by a test function. And okay, let's see it. So I can write it like this. I actually want to write it like this. It's going to be equal to minus ct, okay, maybe, yeah, 1/2. Yeah, okay, let's just do this. Vt square, where ct is the covariance matrix of zt given nu t, and vt is the integral of x minus b nu t phi x d t. So, I mean, this is really kind of by definition. Why? Look what we have here. We have some vector dot zt variance. So what's the variance of a vector dot a random vector? It's like taking the covariance matrix of this random vector and plugging this vector from both sides. And the vector that we have is exactly this vt. Okay, so if you want, like, this is maybe if you want it, I can write it like this, like vt ct vt, which is the variance of zt in the direction vt, and vt is exactly this. Okay, I mean, there's really nothing happening here, but I'm doing it slowly because I feel like, you know, Digesting this is kind of
Maybe a
digesting
better,
the.
expression for me, but,
This one.
Yeah, you have it's a Berliner form.
Yeah,
And you can see, you can relate
I
it
agree.
to the norm of city.
It's a better expression, but for what comes next, this is gonna be a better
But
expression.
at any rate, it's
For
clear that since VT is arbitrary, right? I mean, it's
Yeah.
depends. I don't know why you call it V, it looks too much like new, but.
U, let's call it U.
Okay.
Yeah, I agree. V is the best notation. U.
Also in the definition.
Yeah.
So we don't know, right? I mean, we don't really know UT, so you'll have to take the worst case, and then it's obviously related to the norm.
Yeah. Yeah. Okay, so am I going too slowly? I feel like I'm going pretty slow. Okay, so now kind of so far everything was just equalities. We had no inequality whatsoever. This is going to be the only inequality that we really have in our, this demonstration of the framework, but really like for this framework works for many other things. And ideologically, we just have this one inequality in all of them, more or less. And well, I want to upper bound this thing, right? I want to say the variance does not decrease too much. Let's upper bound it. So what is this? This is the integral of CT to the 1/2. And now I have x minus b mu t, phi of x, d nu t, norm squared, right? This is exactly this by definition. This is just equal, well, the norm of a vector is like the supremum over all unit vectors. This is still an equality, the inequality does not appear yet, of the integral of CT 1/2 x minus b mu t dot theta, and then I have this phi. And squared. I didn't do anything, right? The norm of a vector is like the supremum over this vector dot some unit vector.
It will be the same vector.
It's actually the same vector normalized. Yeah. But now, yeah, I mean, sorry for. Okay, but now comes, okay, if you just want to get one thing from this talk, it's this. It's this really simple application of Cauchy-Schwarz, where, well, I look at, this is the integral of this times this, so it's less than, like, the variance of this times the variance of this. So it's less than the variance. Maybe let's, yeah. The variance of, or how do what's the compact way to write it? Maybe let me just write it like this. CT to the 1/2, the covariance matrix of mu t, CT to the 1/2. Theta, okay, good. Plus times the variance with respect to mu t of phi.
Again, supremum and theta.
Yeah, sub theta. okay? And
Explain again what happened here? How?
so I do Cauchy-Schwarz and I get like a square here and a square here. And this, I mean, the integral with square here and the integral with this square. This
Under the supremum?
I do the Cauchy, for every theta, I do a different Cauchy-Schwarz. And then I get the, like, what's the integral of this square? It's just, I mean, this is just, you know, some x distributed according to some.
It doesn't
This
matter,
measure.
but you wrote the square in a weird place for this Cauchy-Schwarz. It would have been nicer to write the square inside the supremum.
Yeah, but it's also correct.
Yes.
Okay, so I mean, now we take the supremum over theta and boom. I mean, so this is where the covariance matrix suddenly arises. So this is just equal to CT 1/2, the covariance matrix of nu t, CT 1/2, operator norm times the variance with respect to mu t of phi. Okay, so I mean, all of this proof I could have told you in like 5 minutes, but I feel like you wouldn't get like a good intuition for why things are actually happening. You know, you don't, for this particular proof, you don't need all the framework of localization schemes. But when you have the framework, you will see that this proof works in many other places. Okay. And I mean, you see, this is really nice because what we got eventually is that the expected variance after a step is like the variance minus something, which is like, again, the variance times something else. So if we connect everything together, we get that the expected variance with respect to nu t plus 1 phi given nu t is at least the variance with respect to nu t of phi. And here I have 1 minus, and my epsilon of the contraction is just this thing. Of nu t. Okay, let's actually call this psi t. Or actually, let me call it eta times t, which will be kind of consistent with.
So this in particular forces the variance in CT to be not too high, otherwise. Yeah.
Right. So
this evolution to
yes. So this gives me that I need some kind of trade-off. So if the variance in ZT, the higher it is, the faster the process converges to wherever I want it to converge. But this variance decreases faster, and I want to kind of keep those covariance matrices along the process not too large, and choose ZT so that, you know, so that in the end, both this is small, but also the process like converges to what I needed to converge. Okay, and the coordinate by coordinate process gives me a very particular CT. And I mean, CT just depends. We had the formula for the coordinate by coordinate. It turns out that, I mean, this is again just a completely direct calculation for the coordinate by coordinate. We have that CT times the covariance of nu t. So CT also only depends on the center of mass of nu t in the definition of the process. 1/2 CT 1/2 is just equal to what we called, I mean, okay, this is actually equal to the correlation matrix of nu t, which is just the matrix whose ijth entry is the correlation between the coordinate I and coordinate j, like the covariance over the product of the standard deviations. So we really get like a nice, you know, this, I mean.
So this doesn't depend on phi, or whether this.
It doesn't, yeah, the Cauchy-Schwarz killed the dependence on phi.
Yeah, that I see, but in this, so you seem to need just a bound on the correlation of μ, or it seems that in all these proofs you need a bound on exponentially many correlation matrices.
So yeah, so this is basically a way to get rid of the dependence on phi and say so now I consider I have this process. I started from Azure, I have this process, I say something about the process, and this gives me something about every test function. Yeah. And like this structure of proof actually appeared in a series of talks I gave here exactly a year ago. So those linear tilde localizations, you can get from them the coordinate by coordinate localization. But all of these calculations are, I mean, we didn't use it at all. The only place where which linear tilde localization appears is in this matrix CT. And I'll, like, after the break, I'll define a continuous version of those linear tilde localizations where ZT is kind of like the increment of a Brownian motion. And then essentially the same ideology gives you like an analysis for log-concave measures on Rn. But before the break, maybe let me just kind of summarize where we got. And so where we got here, now like the framework by Anari and Oveis Gharan immediately follows. So their theorem just says that we get some variant of their theorem, actually. But I mean, it's really almost the same thing. And so what we get from all of this that if eta I is defined as the maximum over all U, I look at all pinnings such that I pinned I coordinates exactly, and I look at the U pinning of my measure and check the operator norm of the correlation matrix. So what is this? This is just like, we defined this before. I have a vector which tells me every coordinate is either pinned to -1, pinned to 1, or is remained free, and R of U of nu is just like the conditioning to this subcube. So suppose that for every conditioning of I coordinates, I have that the operator norm of the correlation matrix is bounded by some eta I. Then, like, what we get is that the spectral gap of P Glauber dynamics of nu is at least as big as this telescopic product that I get from the variance contraction. And I know that this is like the various contraction bound. So just get product I goes from 1 to, sorry. This is not equal to the correlation. I gain a factor of 1 over n minus t here. Sorry. So this would be the correlation if I kind of localized over all coordinates, but I only choose one of the coordinates. So I didn't tell you, you know, this calculation, but this is what comes up. then you get basically what so a version of the ALO theorem, which is just 1 minus 1 over n minus I at I. So in particular, if all of the eta i's are O of 1, if all of the correlation matrices are bounded by O of 1, then this is like poly, like 1 over poly n. Okay, so I think it's a good time for a break, unless there are questions. Yeah.
So this last statement, it almost seems a little wasteful when we go from the correlation of nu t to eta, because there, I mean, eta is taking all possible pinnings, whereas nu t it's coming from a specific stochastic process. You can imagine that would actually be much better than your eta. Is it true in practice?
It's a great point. So yeah, yeah, it's a great question that I don't know how to fully answer.
So do you have like any?
I mean, we actually are writing a subsequent paper that deals with like also this question. So in some cases it's enough to, but yeah, it's not true that it's just enough to assume this bound in expectation. Because it could be that your test function phi is kind of concentrated in a very small portion of the space. And what you need is a bound on this thing conditioned on the event that, you know, the localization goes into the places where phi is interesting. Yeah. So in general, I mean, I can't say much more than like, you need an almost sure bound.
Sure, but in like some specific, your favorite cases of stochastic localization, which you can really get your hands on.
You can also kind of play with the localization by, you know, choosing the order of coordinates. So we actually don't care what the order is as long as the last coordinate is uniformly distributed. And we can also play with these things, but I don't have many good examples where this is very useful. So there's something, if you have something called a warm start, which means that the variance was like the KL-divergence was not too big at step 1, then like you only need it in expectation. This is kind of almost an observation, but yeah, but it's a great question. Okay, let's take a break.
Another question. You're only treating the Poincare colony, the spectral gap.
You can also do log sub.
Yeah, that was my question.
Yeah. So I'm going very slowly, but log sub is, I mean, you basically can do the same calculation for entropy decay.
Yeah.
And also like covariance structures come up. But what you need actually is not a bound for the covariance structure. It turns out that you need a bound for the covariance structure for all tilts of your measure. So under any external field, you want to say that you have a bounded kind of correlation structure.
Kind of coming from your ZT in a sense? Is it kind of coming from your ZT in a sense that this has to be for a tilt, or is it something else?
It's actually it's a bit different. Okay, it's like the ZT is just giving you a covariance matrix, and you kind of don't care so much. Yeah. But like when instead of variance you have entropy in the calculation, that then here we just had a test function and we wanted like the variance of the test function with respect to the measure mu t.
Yeah.
But for entropy, you have to first change your measure. It's like instead of a test function, you have a change of measure. Yeah. And what we want to say that with respect to this change of measure, the center of mass does not move too much. Okay. And then by the principle of maximum entropy, this change of measure can just be a magnetic field.
Yeah, okay.
Because you just and yeah, and like now we think you basically got everything. Like what I just said is like there's no more than this in the framework. So what you get is you basically want to say, if you do if you apply an external field, the center of mass does not move too much.
Right, okay.
If you have an inequality of this form, then you get log solve.
I see, okay.
Yeah.
In this calculation, phi is still we're talking about the one factor, right?
No, you don't need it.
In this calculation, well,
Subtract the average, right?
yeah, you can just subtract the average.
It does,
So-
it
But
does
then
it
how
for
do
you.
So-
you get the second variance?
So if you look at this, yeah, I mean, I guess I kind of like half skipped a step here. I can take phi and I can add and remove any constant I want, simply because this integrates to 0. This integrates to 0 by the definition of the center of mass. So I can actually assume that phi is centered.
I see. I see.
Yeah, like what I really meant is, you know, it's like a Cauchy-Schwarz really says that, you know, the correlation is less than the product of variances, not just the product of second moments, right? If one of the terms is centered.
Yeah, one of them.
Yeah.
So what do you do in, how do you embed it in a linear space if you have a post-model, for example?
This is actually easy because
So you move to complex. Or
you just take you take the
just indicate
simplex.
those,
Yeah, exactly.
say color is 1 or color is 2. It just
Yeah.
It's another Buddha, it's another cube multiplied by the number of colors.
Yeah. Yeah, you can do that, but you can, I mean, it's actually, it'll work, but it's a bit, for me, it's a bit more natural to say like, I mean, okay, I just need to tell you one coordinate. One coordinate is going to be one of the standard basis vectors, E1 up to EK. So, I mean, I just take like
it's the same
the unit, so it's not like I take the K hypercube.
Yeah, you don't need the
I just take the
unit
simplex.
vector,
Yeah. Okay. I mean, but it's, yeah, obviously it's the same.
Okay.
Yeah. So this we didn't even write actually, the Potts model, the fact that you have a natural embedding. But
Somebody else could.
am I going slow? Or
It's as far as I'm concerned, but you
Yeah.
can ask, people will ask
Yeah.
questions.
No, I definitely wanted to do like much more than this, but yeah, I feel like it's better to like not say too much and but
What is this project about?
kind of maybe.
And you said we should.
Progress of the net. All their markets. Sounds cool.
In many references to Cheyenne,
Fine.
they say his last name is Gharan. And some say it's Gharan and some it's
So I know that this paper is ALO.
Yeah, I know. I think that's the right one. But in many times.
But there is no Kui commented to me that there is no dash.
Now that's it.
Yeah,
Wait, what? I would have thought it was
it's a space, not a dash. Like here.
So, but Oveis is not his middle name.
What?
Oveis is still not his middle name.
No. This is a last name that has a space.
So that's space, okay.
Is there like a convention about why it is a dash and why it is a space?
Yeah. My first name has 3 spaces, so I can't complain.
You have 3 spaces in your last name.
My first name.
In your first name, 3 spaces.
It's only 2 letters.
Are they consecutive?
No, they're not consecutive.
If you know this, well, Tom Leonard, before one of his songs, he was telling a story of a weird guy that was called Henry. It was so weird that he spelled his name H-E-R-3-R-Y. And the 3 was silent.
Oh, yeah.
I guess in your case, the spaces are silent. So whenever you're ready.
Okay, great. So let's consider one more family of localization schemes that's useful for actually both measures on the discrete hypercube and on Rn. And this is, family of linear tilt localization schemes. And those are all the linear tilt schemes where our linear functions have infinitesimal slopes. So we're just going to define it like this. It's actually going to be a stochastic differential equation, but I'm going to write it informally because I'm not actually going to do much with it, just kind of describe what one can do. So before that, we had nu t plus 1 over nu t of x, and now I'm just going to write nu t plus dt over nu t, where you should just imagine dt as an infinitesimal increment of time. And this is going to be equal to, again, exactly the same thing, 1 plus x minus b nu t. And here, I'm going to take any matrix I want, CT. So CT is going to be any driving matrix. It's like the matrix that drives the localization process. It can be anything that depends on mu t. And here I'm going to write dbt, which is, formally the increment of a Brownian motion, which you should think about all of this as like a normal variable, which is centered, and it has covariance CT dt. So it has an infinitesimal covariance matrix.
It's a PSD matrix.
So CT-dBT, it's going to have, sorry, CT transpose CT, yeah. And I mean this it's adapted to. So the point is, I see the measure nu t, and I want to do an infinitesimal tilt. I decide on whatever covariance structure I want, and I multiply it by an infinitesimal Gaussian, and so on and so forth. And this gives us a continuous evolution on the space of measures, which Well, turns out to be pretty useful.
Adapted to nu t means that the expectation it should be 0 or something like that.
No,
The
no,
expectation,
it's
I mean, your
Adapted to, I mean, in expectation anyway, it's 0 because of this DBT.
what
but,
do you mean by adapted to nu t?
It's
The direction.
I can't look at the future and see like, okay, the Brownian motion is gonna do this and that, and in the future, then I wanna, you know, do some big thing in this direction.
Okay.
Okay, so I mean, it can be like adapted to the filtration, but let's say it's just a function of nu t. You look at the current time and you decide how to.
So, you know, what kind of localization scheme of this nature will lead to the, I don't know, the bulwark on convex bodies?
Great, yeah. So this I'm just going to kind of write without proving anything. So yeah, a natural question is, this gives rise to some dynamics. Which dynamics does it give rise to? So first of all, if CT, I mean, it's more general than what I'm going to say, but if CT, you can just take it to be the identity matrix if you want. This is, this actually is, you get a pretty natural process that you can, there are other ways to look at that.
What will you pick tau to be in this case?
Good. So if CT is the identity and tau goes to infinity, for any tau, you get a discrete jump process, but if tau goes to infinity, you get Langevin dynamics. Okay, so CT equals to identity, tau goes to infinity in some, you know, I'm not going to be very precise here. You get Langevin dynamics. I will tell you what this is after I tell you what happens for tau, which does not go to infinity. So CT identity and tau fixed, what you get is, I guess, what now the community calls, and it's kind of nice because only 2 years ago, this dynamics first appeared in the literature, and somehow it reappeared in our framework. What you get is the restricted Gaussian dynamics. So, which is a Markov chain due to I always forget the middle name there. Sorry about this. So Intatli, Ruki, Shan, and Kevin Tian. Yes, 2020. They wrote a paper where they defined this dynamics as an algorithm, and we just noticed that you just can get this as the dynamics associated for this. And what is the restricted Gaussian dynamics? Let me define it to you. Okay, here. So RGD from X of like, okay, maybe P restricted Gaussian dynamics with some parameter eta from X to Y for a measure mu on Rn. It could also be on the discrete hypercube, is the following. So I'm just going to write informally what the procedure is. So we start at a point X, we take a Gaussian Z, which is centered at X and has covariance matrix eta identity. So first we apply some Gaussian noise, and at the second step, take y, which is by distributed according to the law let's call it mu z eta of dx, whose measure is proportional to just again a Gaussian z minus y squared 1/2 eta times mu of dx. Okay. So we start from a point x, we apply a little Gaussian noise to it, and then how do we choose the next point? According to a Gaussian measure centered at this new point z with the same variance, but multiplied by the density of mu. Okay.
This we should see that converges to mu.
No, I mean, it's very straightforward to check, but I actually don't have a good, it's a calculation. Yeah, I don't have a good intuition for why this converges to you, but for why, this is a reversible chain with stationary.
Eta was 0 and z is x. Do we see then that it converges to?
If eta is 0, then it's okay because it's huge Gaussian, and you just kind of multiply. So like this is basically constant, and then you get mu itself. Great.
Okay.
And if those are very, very small jumps, then basically what you have is some kind of Brownian motion step, plus like this thing can just only kind of depends on the logarithmic gradient of mu, and you get, I don't want to write what Langevin dynamics is, but it's kind of like Brownian motion plus a drift, which is the logarithmic derivative of the density of mu. Okay. Yeah, so
what did they apply to? What did they want to analyze using this restricted?
Great.
So
what they do, like their idea is you have, okay, great. So to implement one step of this dynamics, you have to sample from this thing, which is the original measure, but we reweigh the density by a Gaussian, which for log-concave measures is usually very helpful, where you add kind of this makes the measure very, very log-concave. Like if we take these two together, then the Hessian of the potential becomes like very, very big. And it's usually, I mean, we're not going to get into this, but it's usually much easier to sample. It gets easier and easier as you have a good Hessian. So it's kind of, you reduce a big measure to this one step, where this one step is a very localized measure, where you can make an assumption that this is very curved, and then you want to associate. Then you want to say, like in the outer loop of the algorithm, where you do steps of this thing, you want to say how fast this mixes. So you just want to say that for a given eta and the class of measures, I don't need to do many steps of restricted Gaussian dynamics. And what they show in their paper, among other things, is that like if the measure is log-concave to begin with some modulo of strong log-concavity, then you don't need so many steps. And we basically reprove what they have in a slightly more general form, but it's a 3-line proof. Like what you do is you basically do variance contraction, or actually entropy contraction, which gives almost the same formulas. And you get that you only care about the covariance matrix along the process, exactly as before. And this covariance matrix is bounded by something, because this is like, it's well known by something called Braskamp-Leib, or I mean, actually Bakri-Emery, both of them work, that like you have bounds for the covariance matrices. So you kind of get, I mean, yeah, I don't want to, spend too much time on this, but it's really like you plug in some very well-known and easy things, and you immediately get like that this dynamics has a good spectral gap and modified log Sobolev inequality.
And what do you get from this? Like faster volume computations or what?
So
applications in this place?
So in some cases, this gives you, for some classes of structured distributions, this gives you better sampling. This was already known in it's actually, they have 2 papers that use this. And I mean, this was already known in their papers, but like we have a simpler analysis of this dynamics.
So what is eta when tau is fixed?
What is so you can take any eta. This will give you different dynamics. And you want to optimize over it somehow.
It does have to be the same in every step also.
Yeah.
No, you said that if you set CT to identity and you fix tau.
How is tau related to eta? Yeah. Good. Eta is 1 over tau. Yeah.
Okay. So that's why you meant when tau goes to infinity. You spread. Okay.
Yeah. Eta is 1 over tau. Good. So the last kind of component of about all these things, I would say like there's so Amal asked me in the break, like what happens if you wanted to get log Sobolev instead of spectral gap. So all of these things kind of, for log Sobolev, you have like kind of parallel things that you can do as well. So I wanted to actually kind of do some of this, but I think I don't have time. So in the time that I do have left.
It's an analysis where at least, the log Sobolev analysis, if you have a bound on this, you can have a better control of this probability of elements you start with.
Right, exactly. Instead of log of the probability of elements, you get log, and this gives you optimal mixing times. But yeah, I'm not going to touch that. Instead, I will give you another way to kind of extract something from this framework, which is what we call annealing via a localization scheme. And this is the following kind of addition to the technique. So suppose we have 2 localization schemes on a space omega, L1 and L2, say the coordinate by coordinate and the stochastic localization driven by Brownian motion. Okay, take any 2. Then
These are 2 different omegas.
Not same omega.
they both work, both of them are perfectly defined on the discrete hypercube, if you want.
It's what the Brownian motion is.
The discrete hypercube is embedded in Rn. I can do exactly the same thing on the discrete hypercube. Okay.
Or it can be just 2 different ones on the discrete hypercube.
Yeah, it can just be 2 different ones on the discrete hypercube. I can concatenate them by saying, okay, I can produce a new localization scheme by saying I'm running the first one up to some fixed time, and then the second one starting from the measure that I get at that time. Okay, so given 2 schemes L initial and L final, we can define concat, and concat of L initial, L final, and some time t in the obvious way. Okay. By running Li up to t and then Lf up to time infinity. Okay. What is this good for? So sometimes it turns out that sometimes it's actually very helpful, and it's going to help us in the following way. Suppose that we want to get some bound for the dynamics given by LF. Okay, say LF is the coordinate by coordinate localization. It gives Glauber dynamics, and we want to get a bound for the spectral gap of Glauber dynamics. Okay, but if we just run LF, then we don't get good bounds using variance decay for whatever reason. Okay. But it turns out, but suppose that there is another localization scheme, Li, that if we just run it a little bit and then run LF, then suddenly we have much better things for LF. Maybe Li, I don't know, it kind of fixes the measure. It outputs something that is kind of, you know, tame in the sense that.
It's like in warm start.
Yeah, exactly. Like gives us a warm start for this localization, if you want. Okay, gives us something that's amenable to analyzing LF. So, okay, what you can say is, okay, great. So don't run LF, run Li and then LF, and then you have the analysis for both. But if you do that, you don't actually get the same dynamics. You don't get the dynamics coming from LF, which is what you wanted to analyze. You get the dynamics coming from concat of Li and LF. But it turns out that a very nice thing is happening, that there's a large class of localization schemes such that any bound for concat immediately is translated to a bound for the dynamics given by LF.
Will you give us an example?
So yes. So I'm just going to state like, okay, so for this I need the following definition. So what I said now works for a class of localization schemes called dub localization schemes. So what is a dub localization scheme? It's a localization scheme that can be defined by picking a random point from the measure and then picking a random filtration on the space and then conditioning on gradually on like the scheme just comes from conditioning with respect to this filtration. So coordinate by coordinate localization picks a point, takes a filtration which just, you know, you take a filtration where you reveal coordinate after coordinate according to a random order. So it's a random filtration. And the localization scheme is just like what you get from the point and the filtration. Dub localization scheme is whenever it's of the form. So I don't have much time, so you know I'm mostly waving my hands. One, pick x according to mu. Two, pick generate random filtration ft. Filtration on omega. 3, define mu t to be, law of X conditioned on, okay, this is a, like a,
So it's a general revelations.
yeah, any revelation scheme is a localization scheme, and yeah, great, actually, much better term for this. Okay. Good. So a pretty easy theorem says the following.
So this is some just a different, but you can reveal rather than coordinates of X is a sequence of random linear functions on X.
For example, yes. Yeah. All of this will work. So theorem, informal, and it's again, everything, like the proofs of the components of the framework are pretty easy. Suppose that, first of all, Li has a good variance decay. Maybe let me, okay. Suppose that first of all, the expectation of the variance with respect to nu up to this time where I change from Li to Lf is at least like some epsilon times the variance with respect to nu of phi for all phi. So suppose that running the first localization scheme, I have not completely contracted my variance. And suppose that, suppose that with respect to the second localization scheme, every output of the first localization scheme has a good spectral gap. So the expectation, even only in expectation, it's enough. Lambda of P coming from Li and T of mu. So this is like, you know, this is F, the final, and some top, of nu at time T. Okay, good. This is the output of the first localization. And I look at the dynamics given by the final localization, and suppose that the spectral gap is at least delta. Then you get the product. Then lambda of P final dot now of the original thing is at least delta epsilon. And the reason that this is true is, like, just to say it in two words, the Dirichlet form corresponding to the final scheme, when I look at it, how it evolves with respect to the initial scheme is a super martingale. So somehow the Dirichlet form is contracting, so I can just replace this one by that one. But let's not, I mean, it's really like, to prove it, it's really like a few lines. And this is under the condition, this is under the condition that we have a double localization scheme, the Filament scheme. Only the second one, yeah. LF is dupe. Okay, so good. So this gives me kind of a scheme to, if I can't prove inequalities, if I can't prove a variance contraction, then maybe I can first annihilate with respect to something else. And there's several ways to apply this. And let me just kind of go over them without really explaining, all the details. So the first, applications. So first of all, it turns out to be pretty useful to use the continuous stochastic localization driven by Brownian motion as an annealing scheme for Ising models. And the reason is that the following: suppose that nu t is just the stochastic localization driven by a Brownian motion. Driven by Brownian motion and with respect to some driving matrix CT. It turns out it's actually a fact that follows immediately from Ito's formula that we define nu t as this strange evolution, but actually there's essentially a closed formula for what nu t will look like. So nu t x over nu dx is going to be proportional to x minus the integral between 0 and t of x c so when I run this thing squared, when I run stochastic localization, I actually get a measure at any time t that can be expressed as the measure at time 0 times this quadratic e to the minus quadratic function. And the quadratic part is just the integral of this driving matrix. So what a very natural thing, like a natural thing to do if you have this formula is to say, suppose that my measure at time 0 was an Ising measure, so it was just like its density looked like a quadratic matrix. I can just make sure that this term cancels out the quadratic matrix of the Ising measure that I had. And by doing this, I can basically do annealing in a way that after the first step of the localization, I just get a product measure. So it kind of gives me a way to express any Ising model as a mixture of product measures. And given this theorem, we just want to say, in the initial thing, we don't have like a big variance decay. And I just showed you how to establish variance decay, right? You just need some bounds on covariance matrices. And and then in the second step, you just need, basically do Glauber dynamics for the product measure.
So it's only in the ferromagnetic case, I guess.
So, I mean, there are several cases. I mean, everything I said is true all the time, but you still need to analyze how much the variance decays.
Which it's a quadratic method.
This is the change of measure with respect to the initial measure.
This is supposed to cancel the Ising part, right?
Sorry, any Ising measure, even if it's not ferromagnetic, you can think about it as a positive definite interaction matrix, because when you add a multiple of the identity, nothing happens.
Okay, good.
Yeah.
What's YT here? This one.
YT is some Ito process.
Okay.
There exists some Ito process such that this holds, and I can actually write a closed formula for YT. Okay. This is the first application, and for the second.
This is a trick that gets to be up to the critical temperature. This trick is.
This gives again pretty easily. For example, it gives. I'll tell you two things that it gives. One is for the so-called Sherrington-Kirkpatrick model, when you have random Gaussians in the interaction matrix. It recovers like the optimal mixing time, which was, there was a paper of myself with Freddie Keller and Ofer Zeytouni. We gave like the spectral gap, but not up to the critical temperature, only like 1/2 the critical temperature. And then there was another work that used an extension of the spectral independence framework by Anari, Keller, Pham, and Wang, and Jane. Okay, I mean, I actually wrote their names in the last time. Anari, Jane, Keller, Pham, and Wang, who kind of extended what we did to log Sobolev. And this reproves the results, but in a much easier way. Like really, like given the framework, it's just this is one, and second, this more or less reproves, it gives a variant, which is sometimes stronger, sometimes weaker than of a theorem by Roland, Bauerschmidt, and Delgalia, which for ferromagnetic Ising models basically says if you have a ferromagnetic Ising model with a bounded covariance matrix, then you have log Sobolev. So you also get it pretty easily from this. Okay, so this is the first application, and the second application. I know I just have less than 10 minutes, but the second application is for the hardcore model. So if you want to sample independent sets, so I'm just gonna tell you, it gives the first optimal like bound for sampling with Glauber dynamics all the way up to critical temperatures in all degrees. So kind of everything you want for the hardcore model. Incidentally, in the same week we uploaded the paper, there was another paper who proves this, but I think it uses the spectral independence framework, but it needs like, I guess, more technical things to work out. For us, it's just kind of like use the framework in a pretty straightforward way. So maybe if I already said it, let me give just a few credits for the hardcore model. The first paper by ALO basically gave a polynomial bound for Glauber dynamics, and then there was an extension by Chen, Liu, and Vigoda, which gave like a log Sobolev in bounded degrees, and then there was another extension by another Chen, Fan, Yin, and Zhang, which gave like something for any degree, and then there was this paper by the guys I wrote before, AJK. DV, who gave that you can sample optimally, but not with Glauber dynamics in another demo. So there's like a pretty long series of works on this, and now this basically, okay, now we basically have the optimal bound with this framework, and okay, so finally I can just give you the idea. The idea is to use another localization scheme that's very useful for the hardcore model, and we call this the fields localization. It's also a linear tilde localization. And this is a family of localization schemes that's defined as following. So given a deterministic function v of t, so it's like, so let's say from the time axis to Rn. And I'm thinking about it as a deterministic curve of external fields. Okay, so there exists a process u of t, where u t is a pinning such that if I take a measure nu, if I take the measure nu and then tilt it by v of t and restrict it by u of t, then this is a localization process. What is the tilt and the restriction? The restriction I already defined. It's just, you know, the pinning according to this. And the tilt is just like TV of nu is at x is the measure which is proportional to nu x times x of v dot x. So this is just like, you know, do an exponential tilt. Sorry, I feel like I'm really going fast now, but I'm almost done. So given any deterministic curve of external fields, I can, I can just apply external fields to nu. This is a deterministic process. Obviously, it's not a martingale, right? But there is a process of random pinnings that kind of compensates for those tilts in a way that what we get eventually is a martingale. Okay. And
so what would it be? I mean, just for doing something very, suppose this V is just a rotation in the plane. The fields are
V is a vector.
It's a vector, yeah. So it's a vector, yeah. So it's a vector rotating in the plane, just 2 dimensions. I'm just trying to understand how pinning will help you compensate for something.
So let me give you another example instead of the rotation. Suppose that V of t is just t times the all -1 vector.
So the direction is fixed.
So I kind of like, yeah, the direction is fixed. So I just tilt, I want things to be tilted. I want the external field. So this is what works for the hardcore model, because if any one of the coordinates has a very low probability to be in the set, then the interactions between them don't matter so much. So what we want is to apply external fields that just tell you, you know, in any case, you don't have much probability for any coordinate to be equal to 1. And but to compensate for this, some coordinates need to be pinned to 1, because I'm moving them to minus, I'm kind of pushing them to -1. So something has to give. So this, I will have a random process making them jump to +1. And it turns out that, this is like very natural for the hardcore model, because negative tilts are good because of what I just said. And positive pinnings, well, if I pin something to +1, I don't care about it anymore. And I even don't care about its neighbors. So this is what we are annealing with. And it's actually very inspired. So obviously it's not written anywhere, but the dynamics it gives rise to is called the field dynamics, which was introduced by these people. So And this is something we actually didn't know. It was not so straightforward to check that this is the dynamics you get. So what they do is they kind of analyze the dynamics and then compare those dynamics to Glauber dynamics in some way. And I mean, so conceptually, they also use the fact that it's like good to apply these fields. But other than that, like the proofs look very different.
So but still, this is using the theorem about concatenation of.
Yeah.
So this will be the first one.
Yeah, this is the first one. The first one is the does annealing, which basically gives you a strong external field that makes your measure kind of not care about the interactions, and then the second one you can
you get a bound on the original global dynamics.
Okay, I think this is a good time to stop.
Okay.